with the next talk? Yeah. All right. Thank you, Sergey. It was a really interesting talk. Thank you very much. All right. Amy, if you want to join the Zoom, okay, you're in. Nice. Perfect. Okay. Yeah. So this side, and basically you share screen from your computer, you click through on your computer.
Okay.
And then
when you move this computer or
the computer is moving the microphone also. We can move it somewhat.
okay. So how would people
Just kind of, yeah, we're sharing.
All right, it's a little tight. Oh, wait, so then why do I need to join?
So you share your screen.
Oh, that's right.
So this is, yeah, so the obviously the AV is coming from this computer.
Okay. All right.
And video recordings.
Okay, till we set up, I can introduce Amy. Amy is an assistant professor in the Department of Electrical and Computer Science at UT Austin. She works in various representation learning, improving sample efficiency and generalization and reinforcement learning. She'll be talking about learning representations for planning. Over to you.
Okay, awesome. Thank you for the very kind introduction. I'm really happy to be here and talking about learning representations for planning, and specifically, for the setting where we want to move beyond rewards. And so first, I kind of want to talk about, why should we care about representation learning? And maybe like a more specific question for this talk is, what makes representations amenable to planning, right? What do we want out of a representation if we know that our end goal is to be able to do kind of general planning for some domain, for some environment with some dynamics, right? So what do we want? We want a representation that only captures the relevant information, right, for any task that we may care about in that domain. But that's just about what is the information content. That doesn't really talk about like, how is that representation structured? What states should be near each other in our representation space? Like, what kind of structure should it have? And so, maybe one really simple idea is we want our representation to be structured by reachability. We want states that are very reachable, that are close together temporally, maybe for some specific policy, to be also near each other in this representation space. We want maybe a representation where some distance metric in that representation space corresponds to a value function, so that we have a notion of progress associated with that representation. And then kind of an open question is then, so the next question is, so if for me to be able to construct this kind of representation space, how am I going to get good value functions for every possible downstream planning task? And so I'm hoping that we have some works that I'm going to talk about today that try to tackle some of the problems to kind of get us to this kind of nice representation that has these properties. So first, I want to talk about this work that we did a while ago. Actually, this is from near the beginning of my PhD, kind of before I had really seriously thought about representation learning for RL, and we kind of had some early ideas like related to this, but I couldn't necessarily articulate them as well. But I think this Plantivec work like fits in actually really nicely into this talk. Then I want to talk about quasi-metrics. So that was something that Sergey had mentioned as well. So in the goal condition setting, your value function is always going to be a quasi-metric. And so a quasi-metric is something that we can actually embed in this representation space that now is going to give us this kind of general goal condition value function. So we're going to talk about like how we can leverage that idea, that structure. And then finally, I want to talk about value implicit pre-training. So this is, again, kind of like scaling things up, scaling these ideas up. Also similar to Sergey's talk, also kind of like, how do we deal with action-free data? How do we pre-train on video data in kind of a self-supervised way that makes it useful for a lot of downstream tasks? Okay, so with that, let's just launch right in. So Plantivec was built on this idea that if we have a bunch of states, and here we were just dealing with high dimensional observations, so just images, with some local metric D, then the graph G weighted by D is embedded by a Riemann manifold, right? The metric of which is the shortest path distance, right? So all this is really saying is if I have a bunch of transitions, I can take those transitions and construct a graph out of them. And the shortest path in that graph, if I just run Dijkstra's algorithm on that graph, I'm going to get the optimal policy to reach any goal, to reach any state goal from within that data set, right? So a very simple idea. And now we just want to embed that graph into a representation space. We want to take something discrete and make it continuous. And so that way we can now generalize to new states, right? So with Plantivec, the idea is very simple. We just want to treat the construction of this graph as a semi-supervised problem. And so this consists of 3 steps. First, we're going to just learn a local metric. And so this allows us to generalize beyond the transitions that we actually see in our data set. So if we just learn a local metric that, like a classifier that says, are these 2 states close or not? Now we can pass in, we can train this with the transitions that exist in our data set. And then we can now hope that it'll generalize to new states, new pairs of states that don't exist in our data set, right? So we can learn a local metric, we can build this graph, and then the next step is to just perform heuristic search. And now we can just do, now we have a representation that allows us to do goal conditioned RL.
Can you switch on the camera?
My camera?
Yeah.
Okay. Video. Okay. Yeah. Okay. So we have our data. We're going to build our graph. We're going to learn our local metric, perform heuristic search, and then we have a value function. Okay. All right. So for learning the local metric and building the graph, like these, again, are very simple. So we just use a temporal contrastive loss because, again, this local metric can just be trained using a classifier. Are these 2 states close or not? And so here S just represents reachability. So our positive pairs are states that are considered close. So we can just denote some step size K and say, if these 2 states are within K transitions of each other, according to our data set, according to our graph, then they're a positive pair. Otherwise, they're a negative pair. And so, we can just use like a standard info NCE loss. And so now we can also build this graph. So we can add edges between nodes when distance is smaller than some threshold according to our classifier, right? So this now allows us to build a denser graph than we could have just from the original data set. Okay. So now we can embed this into a representation space. And if we actually visualize this, like the t-SNE of this, so if we take just, like a simple grid world, here we just have this little C maze. We can see the global structure in our learned representation here, Plantivec. And then correspondingly, if we were just to train a VAE, we kind of lose a lot of that structure. And this makes sense, right? Because the VAE is not trained to actually capture the dynamics of the environment. It doesn't capture reachability. It doesn't have any information about that. And so it's really just relying on pixel similarity across those observations. So it still like looks pretty structured, like all the purples are together, all of the greens are together. But it hasn't, there's this weird twisting thing going on. It hasn't really preserved distance in the way that we want it to. And so, we can perform heuristic search in this space. And so, as long as we have access to a dynamics model, then we can always say, I know what next state I want to go to, right? I know I can pick some next state that I can reach. And then whichever next state is kind of has like shortest distance to the goal, that's going to be the next state that I go to. So I can perform this kind of like heuristic greedy search in order to reach my goal state. And so we can compare Plantivec's performance against other methods, so we have DQN. SPTM is semi-parametric topological memory. So this was, again, kind of like a graph search-based method from a few years ago. And then random, I think, was just kind of sort of like a lower bar baseline. And Plantivec performs really well because of this structure that we've embedded in the representation space. And the really cool thing is that all Plantivec is doing is we're running Dijkstra's algorithm, right? You can think of it as like we're running Dijkstra's algorithm at training time instead of at test time. Because if we were doing planning with Dijkstra's algorithm at test time, it's just very expensive to have to run that every single time that we're trying to reach a new goal. And so we can look at planning cost, and we can look at And so plan2vec has kind of near constant or linear near constant computation time for as we increase the length of the plan that we need. And it's because we're just generalizing off of the work that we did during training time when running Dijkstra's algorithm. Whereas if you were to actually run Dijkstra's algorithm with longer and longer plans, we can see that this is something that's not really going to scale. So, right. So the key takeaway here is really simple. It's just, we're trying to build a graph from data. And the reason I'm talking about something so simple, a method that's so simple and from 2020, so 4 years ago, is that this is what's underlying, like, I think a lot of the recent ideas in learning representations for planning is really just this very simple idea of you can think about your data, all of your transitions as a graph, and you're really just trying to find shortest path over this graph. And then the question is, how do you do that fast? How do you do that with fast inference? And how do you do that so it can generalize to continuous spaces into larger amounts of data, right? So some issues with this method in particular is that even though we're embedding this in a representation space, we're still running Dijkstra's algorithm at training time. And so we were really limited by the amount of data that we could actually scale to. So like we could get this to work. We had some really cool results with StreetLearn. So this was a data set that DeepMind had put out a while ago, and I don't think it's available anymore, but it was just street view images of various cities. And I think like Pittsburgh was one of them that we actually used. And so we could actually just, plan routes throughout Pittsburgh just based on these street view observations. But we could only do it with like a few thousand data points, because beyond that, running Dijkstra's algorithm to get the training data, it started to get too expensive. It also turned out learning an accurate local metric is hard. So our method was not very forgiving of, so think about it, right? So if your local metric, your classifier has a false positive, it's going to think that there's some edge that exists that it shouldn't. So it thinks you're going to be able to apparate between locations in a city. And if that is a valid edge, it's going to find that edge every time you want to find a shortest path. And so it was very, very important to not have those false positives. And that was something that was actually quite difficult in practice to avoid. So, so those were some issues that like we, now have to solve. We have to think about how to solve. Okay. So one other issue with plan2vec is that we were just learning a representation where we just arbitrarily picked like L2 distance as the metric that corresponds to that to path distance, right? If your dynamics are not symmetric in your environment, and if you're just like walking around a flat city, it's pretty symmetric. Everything is pretty reversible, right? Like going in one direction versus going back in the other direction is pretty much the same. But say you have hills, or say, I don't know, you have like one-way doors. You can go in the door, but you can't go back out the other way, right? Then we've broken symmetry in our dynamics, and L2 distance is not going to be able to capture that. And so this is why, when we talk about value functions and we talk about distances or value functions as distances, really value functions are quasi-metrics, right? So we don't actually want to have that symmetry property that metrics have. And this is a property that's very specific to goal conditioned reinforcement learning. So as part of this, so this work was really just focused on, okay, we know that these value functions have this nice structured property. We know that we can do better than just using, some universal function approximator, just some like neural network to be our value function. We know we can do better than that. We know that embedding a value function in a representation space and then using L2 distance as the value function is the wrong thing to do. So what can we do instead? Right. And so then that's the key idea behind this, is that we actually want to learn a representation with a corresponding quasi-metric for the value function rather than a standard metric. Right. Okay. So this gives rise to quasi-metric RL. And the idea here is that we want to pull apart staple pairs. We want them to maintain, like a notion of global distance that is consistent in the same way that we did for Plantivec. We want to do this in a way where we don't have to run Dijkstra's algorithm at training time. We want to do this with RL. We want to do this with dynamic programming to be able to scale this. So those are all of our constraints. But otherwise, this looks very similar to what we would have done to embed a value function in a representation space, right? So we just want to optimize the quasi-metric embedding, d theta, as a negated value function, right? And then subject to this constraint where we basically don't want to overestimate our local cost. We want to make sure that neighboring states are always kind of like within some distance of each other, like at this epsilon distance. And it turns out that if we optimize for this objective, this objective with this constraint, QRL provably recovers global distances, right? So with sufficient data and model capacity, we can recover the optimal value function for any MDP. So if we look at this in a really simple environment, and we were very careful to pick one where symmetry is broken. So here we're just looking at mountain car, which is really small here in the corner. But for those of you who are not familiar with this very simple environment, you have a little car that starts at the bottom of this hill. You want to reach this flag at the top of the hill. And so you basically kind of need to build up enough momentum so that you can make it up the hill to the top. And so obviously the dynamics on the hill are not symmetric. So here we tried to visualize what the ground truth optimal value function looks like. So for the task of just reaching this flag on the top, so this two-dimensional image corresponds to velocity is the x-axis, velocity of the car is the x-axis here. The position of the car is the y-axis, so that basically just corresponds to the entire state, right? The state space for this environment. And then the color just corresponds to the value, right? So we need some velocity in order to make it to the top. Let's see. So too much velocity is bad because then you're going to overshoot. And so you want there's some perfect velocity. And then this is the X position that you want to reach where the flag is, right? So that's where you want to be. So let's look at what happens when we try to actually learn this value function with various methods. So if we just do Q-learning with the universal function approximator, we get something that looks like this, pretty close. Ensemble conservative Q-learning does something really weird. Contrastive RL also looks pretty close, but doesn't quite look right. Whereas like QRL using this kind of quasi-metric structure, so the quasi-metric structure is just embedded in the function approximator that we're using into the representation space. We get something that looks quite close to the ground truth. This is what it looks like if we were to use our QRL objective with an L2 distance. So again, breaking that asymmetry assumption, and forcing a symmetry that doesn't exist, right? So you can see that we do have that symmetry in the value function that we learn, even though it doesn't exist in the ground truth. If we take Q-learning and add quasi-metric structure to it, we actually get a much better performance. And then here, contrastive RL plus quasi-metric looks a little bit better, but still not quite right. And then these are just more images. So this one is distance to the top of the hill. So this is some other goal of distance to just some random state and another example. And so here are the ground truth value functions for those tasks, and then what we get compared to all of these other kind of baseline methods. All right. So you can kind of think of like what we're learning as this hypersphere, where this quasi-metric latent distance, you can kind of like measure like the latent distance just corresponds to the optimal cost of starting from some initial state and reaching some goal state, ZA, starting from SA and reaching SB, but in this latent space of ZA and ZB. And then the latent geodesic just corresponds to actually the actual optimal plan. Like what are the intermediate states that we need to get to in order to reach that goal state, right? So this is kind of like a more geometric visualization of what we're learning. Right. So planning for a good action just corresponds to knowing the effects of actions in the latent space. You know, when you take an action, where are you going to end up next? And so you can kind of think of this as latent world modeling. We're really just learning a representation of distance, of reachability, but that does capture a decent amount of dynamics. We're not capturing actions, but we are capturing what states are nearby. Okay. So we have experiments in both offline and online settings. So for offline RL, you know, we focus on just these kind of maze 2D environments. We have to guide a ball through a maze towards target locations in various settings. Again, we kind of compare against a lot of state-of-the-art methods of the time. So contrastive RL, MSG, model standard deviation gradients, which uses an ensemble of CQL up to 64 CQL value functions in order to estimate uncertainty and train a policy. Right, we're in the offline setting, and so we have to kind of like maintain pessimism to stay within our data support. Right, so which is why we need to do that. And so that's here. MSG plus hindsight experience replay, and then we have some planning methods using ground truth dynamics, diffusion model, diffuser based baseline as well. But we find that QRL performs very well in these settings, right? So this is the performance that we can get just from leveraging the structure that we know exists in goal condition value functions. Okay. And so with QRL, with this kind of like quasi-metric structure, we can add this structure to existing methods as well. And so here we're adding on, we can do planning with a quasi-metric value function, optimal value function. We can do trajectory modeling with our quasi-metric value function. So QRL value guidance or MPPI, we're using the QRL value. And so we see a big jump in performance when we do that. So that's really nice, is that you can just plug this into various types of RL methods. So this also works with online methods. So for the online goal condition RL benchmarks, we just use this robotics task of being able to like push a block. So these are more complex environments. We now have continuous action. So we just kind of wanted to show that we can scale with these additional complexities. So we have fetch reach from state as well as from images, fetch push, fetch slide. And again, we kind of see that we get like pretty good performance in the very simplest of the tasks, but we do perform much better compared to methods that are not relying on this structure. And again, you know, you can also combine this quasi-metric RL with DDPG, with hindsight experience replay, with behavior cloning, right? So it's something that's kind of method agnostic. Okay, I'm just going to pause for a moment and see if there are any questions at this point in time. Yes. Yes. Yeah, so that was something that I kind of just brushed over. But basically, the kind of like more naive way of incorporating a quasi-metric value function is that you only enforce the quasi-metric structure in your final value function. But when you're doing Q learning, there are all of these intermediate Q functions that you step through, like in order to find the optimal one. And so with these prior methods, they're not actually enforcing that these intermediate Q functions are also quasi-metrics. So something very specific to QRL is that every time we update our Q function, we are maintaining this objective. So we are maintaining the constraints that this has to be a quasi-metric, and which means that the dynamics of the optimization are different. And so that accounts for some of the performance difference that we see. Mm-hmm. Yes.
Regarding plan to vec,
yeah.
What sort of data that's not intuitively thought of as a graph can be converted in this way, if it can be?
So I guess like I tend to think of like transition data in MDPs as something that you can always like structure as a graph. So do you have an example in mind of something that isn't? Okay. So something that isn't a graph.
I guess are there limitations to what this can represent?
Into what this can represent. Good, interesting question. Yeah, I guess like MDPs can always be structured as a graph. So what can you have? So I guess if you have something partially observable, then you cannot, it would have to be represented kind of as like a stochastic graph, right? Because then actually that's an interesting setting, right? Because yeah, as soon as you have stochastic dynamics, the graph kind of breaks down because now with every edge, there's no guarantee that you can actually, right? But then in that case, all you can do is replan every the standard approach is after every step you replan, right? To just exactly. So I you know, you're putting me on the spot, but to that I think that is the approach that we'd have to take with Pontific. Yeah. Okay. All right. Any other questions? All right, another question. Okay, yeah.
This is my first time seeing this line of work, but it really reminds me of, if you're familiar with like learning the graph Laplacian.
Yes.
Very similar.
Spectral methods.
Yeah.
Yeah.
I wonder what, when you were designing this like quasi, what considerations went into that with like the dynamics of that, and why not to use something like, you know, like learning the graph Laplacian, which I think gives you like, you know, it's the same. I'm not sure the details, but it's the same.
Yeah.
You're trying to structure.
You're right. It is very similar, actually. And I've thought about the similarity to graph like Laplacian and spectral methods. Yeah, I guess like the way I used to always think about those methods was that they always depended on some behavior policy. But if you're using a uniform policy, or like as long as you have access to all the transitions in your MDP, then you know you're okay. You're still building a graph out of those transitions. The graph Laplacian, I guess, is just a way you're compressing that. So we know that you're losing information. I think with Plantivec, we are not trying to compress the graph. We are trying to make the graph continuous to allow us to generalize to transitions to states that don't exist in our data set. So I guess to me that seems like one distinction, but yeah, honestly, I don't know those methods like well enough to say if, but off the top of my head, kind of like knowing that like the graph Laplacian is basically a compression of the graph. That's like one distinction that comes to mind.
You should talk to Marlos.
Okay. Yeah. I know Marlos. I'm happy to chat with him. Yeah. Oh, wait, 5 minutes? Okay. All right. Okay, let's talk about VIP. Okay. All right, so this is just scaling things up. This and actually I should say, you know, this isn't like a linear progression of ideas and projects, unfortunately. You know, looking back, if I could have done something more linear, that would have been great, but this was more like a bunch of projects, and then afterwards it's like, oh, there's these nice connections. So for VIP, again, we're just trying to learn this goal condition value function. Now we want to do it without without access to actions. You know, we have video data. You know, I think Sergey did a really good job of kind of like framing this problem. Slightly differently from what Sergey was doing, we are just want to pre-train. So we're not assuming that we have access to both like a data set with actions and some additional other data set. We are assuming that at pre-training time, we just have a video data set, and we want to learn something useful for downstream tasks in any domain. All right, so that's the problem setting. This is, you know, why we should care about universal value functions. Yes, we already understand goal condition RL is so great. So let's start from a specific data set. Let's start with Ego4D. And so this is just a video data set of egocentric camera, like people are just wearing GoPros, going about their day, very complex tasks, right? Like very visually complex and diverse video in this data set. And we want to apply offline goal condition RL to this, right? So this is the standard offline goal condition RL objective. You know, this should look very familiar to you. This is just maximizing our expected discounted return, subject to this constraint where we want to stay close to our data distribution to make sure that we stay within our data support, mathematically sound. What are human actions? Where does AH come from? We don't have them, so we can't optimize this in practice. Turns out, if you look at the dual formulation of this objective, we get this nasty thing on the bottom here, but you see that actions are now gone, right? So instead, all of the components in this objective, we have access to very easily. So we have goal frame, initial frame, middle frame, so transitions, right? Like neighboring frames, we have access to all of these things. So now this can depend only on the offline data, state data, no dependence on actions. And this is now something that we can optimize for with video data. So so when I say, I wish that we'd done something more linear here, like we ended up doing the dumb thing where we just kind of embedded this into a representation space as L2 distance. So ignoring the whole asymmetric dynamics thing that I made such a big deal about earlier. But this worked pretty well in practice for a lot of robotics tasks. So it turns out that this objective also looks a lot like a contrastive objective. You can kind of think of it as we're pushing apart neighboring frames to be some fixed distance apart from each other, while trying to also push together far away states from the same trajectory, from the same video. And so this kind of push-pull contrastive objective in order to learn a representation space that corresponds to a goal condition value function. Now, L2 distance in this representation space corresponds to a dense, shaped reward for downstream tasks. So that we found that this kind of like zero shot generalizes really well to a lot of like image-based robotics tasks. The idea being that because Ego4D is so diverse that like this generalization becomes easy. And then this representation can also be used for states. So what we pass into our policy no longer needs to be some high dimensional pixel observation. It can just be the representation that we learned from Ego4D data, right? So those are how we're going to use these two things. I'm going to skip over this a bit. So one of the first, so the first set of experiments that we had were in a simulated robotics environment, Franca Kitchen, a variety of goal condition tasks, different camera views, different initial states to control for difficulty. First task that we do, trajectory optimization. All right, so we're assuming access to a ground truth. We use MPPI. We're assuming access to a ground truth dynamics model. So this is avoiding evaluating our representation. We just want to evaluate that L2 distance in the representation space as progress, as reward, and see how well it does, okay? And then replan after every step that we take, which is very standard planning practice. No policy learning. And so this is our success rate. And so we're just comparing against a bunch of other representation learning-based methods. So R3M is a temporal contrastive objective-based method. ResNet here is just, I think, like an ImageNet pre-trained representation. So these are all baselines because prior methods had found that these representations work really well for imitation learning with robotics data. So that's kind of why we were comparing against these. But none of these methods are actually explicitly trying to do what we're doing, right? Which is learning a distance in a representation space that corresponds to progress. So that can, that probably accounts for this performance difference that we're seeing. All right. The really cool thing is scaling with optimization budget. So this really shows that the global structure of VIP, of our learned representation, is very nice. So basically, as we increase our planning budget, as we increase the horizon with which we roll out our dynamics model, as we increase our branching factor to try to search for optimal paths, we just keep getting better performance, right? And so that is because global distances are very coherent in VIP. And we don't see that kind of performance gain with scale with the other methods because the baselines are exploiting their unsmooth reward landscapes. Okay, so VIP benefits from increasing optimization compute. So now we can move on to doing something that looks more like RL, so learning a policy, using both the representation and our reward that we've learned in our representation space. So we just chose reward weighted regression. So this is something that looks a lot like behavior cloning. You're just weighting transitions according to the pre-trained rewards. So it's a very simple method, a one-line change from BC, from behavior cloning. And so our hypothesis before we look at the results is that VIP, so our VIP representation plus our VIP reward using reward weighted regression is going to outperform behavior cloning with just the VIP representation. So representation, no reward. So we have some real robot tasks here. And so yeah, basically, okay, sorry, I'm gonna rush. Okay, we get great performance. And then here, the performance difference that we're seeing in these two boxes is whether or not we pre-train on Ego4D data versus this is just from scratch. So this is like 10 demonstration trajectories. So not very much data in our robot domain. And so we basically can't really do anything here, right? And then just some visualizations of the videos, which I'm gonna go through too quickly for you to really watch. And then, okay, I'm gonna end on open questions. So, you know, I think there's still a lot we can do in this space. I think it's a really interesting space. You know, we should think about like what properties do we want out of a representation? I gave some examples. I don't think this is all of them. What type of information should be captured by the representation, as well as how should that representation be structured? What problems are most suited for planning? You know, can we define a purely local learning objective that leads to this kind of global optimality, this kind of global structure? You know, what kind of objectives are there? And so with that, I'm going to end, and then I don't know, maybe I can take one question. Yes.
So let's thank our speakers.
Okay.
Thank you.
And this, most of it is on fully observable setting, right?
Yes.
If we have a partially observable sufficient statistic learner, let's say LSTM or something, and then would extending that with these type of metrics be something?
Yeah.
You have looked at?
Great question. We have not, but again, I think, you know, that was really similar to the question that I got here about like, you know, what are settings in which this kind of graph assumption doesn't really work? And so within the partial observability setting, what the additional complexity you get is the fact that now your edges, your transitions are stochastic, right? Like even if you use an LSTM, they can still be stochastic. So, you know, how well does this work there? I'm not sure. We haven't actually tried that out, but I think it'd be really cool to try.
Assuming you learn some Markovian latent state. And
yeah, but that's a big assumption to make, because if you can make that assumption, that means you really only have a K order MDP, right? Like if you're, because then you're saying, as long as I have K steps of history, I Markov again. That's, you know, yeah, getting that compression right, I think is an interesting problem. But I think the really interesting, like really, you know, if you really want to talk about partial observability, I think you cannot get away from the stochastic transition part. Yeah. All right. Thank you.